Okay, start. So I'm waiting for confirmation. So setting up the sizes of our screen. So let's talk about bridge engineering plan in this particular video. So good evening, welcome back. Good evening, anybody who will confirm our sound check? Okay, so we are live again. We are here at the campus, Taguig City University. So let's move on to the next slide. This is about bridge plans and plan set, organization, and content. So we already talked about this in passing. Now we will take a look today again for the second time, but in much detail. So we will try to understand each and every details of the engineering plan. Okay. So you must react so that we can reply, we can answer your inquiry. React in such a way that you may inform us which part of the plan is not clear, which part you want still additional explanation, and so on. So I hope this plan could be seen clear enough. I'm just hoping. I think it's very small, so I will use a monitor of my own so that I can see if the video transmission is okay. So let us check. I will check it. I am checking it actually. So the video reception is okay, but the plan is so small. So it is so small, we cannot actually understand anything out of this. So how can we make it bigger? How can we make it bigger? Maybe new slide, new duplicate slide. Then how to adjust? Okay. See. You cannot, you cannot, you cannot understand anything. Section, section along column 1. How can we make it a lot bigger? Oh, this one. 70, 80. Okay. So it's becoming clearer and clearer. So let us, what happened? So let us enlarge. Okay, so okay. So now we can now understand some of the text. Okay, are you with me? Can you read something? For example, the text inside the box. Can you read all the text inside the box? The 3 lines of text inside the box. Normal to end bent. Bottom of end bent. Cup to top of RIPrap. Okay? Is that clear? The text inside the box, the small box in the middle of your screen. So medyo blur, sir. Okay, so I will again increase the, I will still increase the percent enlarge. Percent enlarge. Now, what can you say about now? Is it better? Is it better now? Medyo okay na po. Okay, so at least became better. So I will still enlarge it. 2-click enlarge. Okay, so I will still enlarge it 2 clicks so that it may become so we are now 140%. 140%. Okay, we are now 140%. So 140%. So I think it is now clearer. Okay, so it is now readable. So in your local dialect, basable. Basable daw. So that means readable. Okay? So, fill face. Okay? Fill face at end bend. Again, review. What do we mean by end bend in this context? So, we already took it last meeting. Okay? This end bend is part of the substructure. Okay? What is the substructure that we call end bend? Okay? Please state your answer on the comment box below. End bend. So there are two major classification of end bend. That is individual, and the other one is joint. No? Joint with the bridge itself. End bend and the bridge is joint, meaning the superstructure is connected to the end bend as a homogeneous unit. And ISTA. What do you mean by ISTA? Okay. ISTA 88 plus 5.34 grade point. So, we are familiar with that in surveying. Okay. That is a what? Station. Okay, a particular point. Okay, so measured with its what? Elevation. No? Elevation is how much in that specific point. Okay, so that is what? 234.12. Okay, so call 1. What do we mean by call 1? Okay, that's a column. Okay. And that is our what? 88 plus 00 in our survey of the area. Okay, survey. So meaning it is even more complex when we are dealing with what? Roads and highways. Because we need to be precise in our survey measurement. Okay, so geodetic survey must be precise. Okay. Particularly in those countries that have landmass boundary with other neighboring countries. Okay, because it might become a reason of what? Misunderstanding between countries and with result to war, for example. So that's why we need to be precise when we are doing what? Bridges and roads and infrastructure, rather than, for example, a building. We don't even need the sign instead of geodetic engineer. Sometimes they will be asked to comment. We need their expertise, but most of the time it's not necessary. The building official will approve our engineering plan for building permit even without the documents signed and sealed of geodetic engineer. Okay, so that is the minimum. What I'm talking is minimum. Architectural plan, structural, plumbing, and electrical. That is the minimum. So maximum, so it includes geodetic engineer. So this is where geodetic engineer signature is very important. So as you can see, the grid lines, okay, elevation, so on. No? So this is a plan and elevation view. So we have this particular specific point on Earth. Specific point on Earth. Okay? So, what's next on that? Immediately below that group of text, we have what? Begin, front. Okay? Begin, front, slope. Then, sta. That 87 plus 93.21. Again, this is what? This is, as you can see, there is somewhat sort of setback. Okay? Okay? The ISTA 88 plus 5.34 is to the right side. So therefore, 89 plus 00 is to the right side. And if you subtract and subtract, you are going back to the left side. So 87 plus 93.21 therefore is to the left side of ISTA 88 plus 5.34. Okay, so that is the comparison of the measurement, and we can immediately subtract the difference between this station for us to be able to determine the exact distance of this. So there is a exact distance. So it is referred as a specific point on Earth. So with particular elevation shown. Grade point elevation, that is the particular value of what? 233.85. So the first point that we read out, that is 234.12. So you can subtract again so that you can find out the difference in elevation. Okay. That and therefore, so you can notice that is almost negligible if we are looking at the even in the side view. That is almost negligible. You can see it as perfectly horizontal, but it's not. So next below it, we have what? Fill. What do we mean by fill? So meaning we might have what? The excavation before the construction begin, and after construction, we will put back. We will use the excavated soil and put it back to the excavated area. So that means fill. So fill, therefore, as you can see, it is therefore expected to be what? The soil. And when you fill it back, what will you do? You will stamp it, compact it. Compaction of the soil must happen. That is a process wherein we need unstable soil quality. So you might add certain type of particles or type of soil like sand, sandy soil, and stones, gravel, even without the use of cement paste. So by those type of soil alone, it would give us a better quality of soil as a foundation. Okay. Then next to that, just below it, below the word fill, we have 2. If I am not mistaken, that is 2 feet dash 0 inches. Okay? 2 feet dash 0 inches. And below that line, we have what? Min. So that means minimum. Okay? 2 feet 0 inches embedment. Meaning, what do you mean by embedment? That is embedment. It is embed that. Embedment meaning it must be under the soil, the presence of the soil. So that part must be 2 feet under the soil. So below the soil level, below the natural or the final soil that you filled out, compacted. So that is the meaning of that. So it is not what a guesswork. It is what actually being designed. That is being calculated. That is computed actually. That is not a wild guess to have a 2 feet embedment. We have a computation on what geotechnical that would give us the idea how much pressure we need from the soil so that we can put up so much stability in the soil and what amount of embedment. Then next to it, just below, HP 14 plus 73 steel pipes. So there are steel pipes of that size. Okay, so HP. So HP we did not tackle on the steel design, but it is a specific shape, type and shape. It defines a specific type and shape. For example, what is W? What is W steel? What is S steel? Okay, so HP steel pipe is a pipe, but the shape is HP shape. Okay, and then 14 plus 73 is the size. Okay, so is it 14? Can you confirm that it is 14? I think it is 14 plus 73. HP 14 plus 73. You can even what? You can even search for it. HP 14 plus 73. So you can search it online. So that is what? Structural steel and H piles. Okay, so piles. That's why, okay, that is the meaning of HP. Okay, sheep. H piles. That's why it is HP. Okay, that is a specific shape. Okay. So it may even look like W. I tell you, it looks like W, but it is structural steel and H piles. Okay, piles, H pile. The shape is H. Although, if you turn it around about 90 degrees, if you turn it 90 degrees on either direction, it will look like H. But on the standards table, it is actually shaped like an I, letter I. Okay? So they're saying this is I beam. So this is not beam. So this is for pile use. So therefore it is H pile. Okay. So I just confirmed it online. So there are available. So in our figure, in a drawing, it is just pin, no? It looks like a pin because our drawing is so small. It looks like a pin, but actually it looks like a W beam. It looks like a W beam. Then we already know what do you mean by steel piles. Steel piles. Okay, so there are parts of the bridge under the soil. So these are one of them, one of those parts that are under the soil. So footings, foundation, piles, sometimes pile cap could be, and usually, actually, they are under the soil. So there are several components under the soil. So just going to the right of your screen at the top, just below the 88+00 reference. Okay, so that reference grid. So we have what? 1 foot 7 inches minimum berm. Okay, so normal to gap. Okay, we would provide that. Okay, normal to gap. So we need the gap. Okay, so as you can observe on every bridge, there is a gap. And if we are talking of roads and highway, that is those gaps are usually called joints. Okay, we call different types of joints in roads and highways, but a bridge now, because we have several components, we call that gap minimum berm. So berm. Okay, imagine 1 foot 7 inches. Okay, so next we have 1 foot minimum earth berm. Okay, normal to cap. Okay, so normal to cap, just below the first line of the specification. So 1 foot berm. Okay. So do we have next? Just below it is normal to cap. Normal to cap. Cap meaning for example, we have a what? We have a bottle. So we have a cup. So usually the cup is on top. Okay. Another use of the word cup is here. So okay, this is another use of the word cup. Okay. So if you have a head, you will use a cup. Okay. You can use a cup. So particularly when your hair is not good. When your hair is not good looking, you can use a cup. So that is another use of cup. So therefore, if we say cup in the context of bridge engineering, that means it is on top. Okay, on top. Okay, so it is on top. Okay, on top of something. On top of something. So that is what? normal to cap. So if we mean normal to cap, we mean perpendicular. Okay. So that's what we mean by normal to gap. Same is true with normal to gap. Normal to gap meaning perpendicular to the gap. Okay. So what's next? We have what? 1 foot 0. That is what? What is that circle? Okay. So that is symbol. I think that is the symbol for RIPrap, no? Starting of the RIPrap 1.0. Okay, so that is, I think, the symbol for RIPrap, no? Then what's next is slope to drain. So meaning that this particular portion is sloping down, so that every water flooding or flash flood will go to this direction. So that is what we should expect, no? So water coming from here, no? Or on top of the bridge. This is the top of the bridge here. So water will go down here and then slope down to the side. So this is the direction going down the going down below the bridge. Okay. So next to this is elevation 220.0 plus what? Okay. So meaning we have a specific measurement from this point 220. Take note 233.85. Okay, and then this is 220. So this is what in terms of what English units. We are using English units here. So it is in terms of feet. So there is about 13 feet, no? About 13 feet from this point to this point. Imagine that. Imagine that elevation, 13 feet. Okay? Okay, imagine that elevation. And actually, these piles, this is actually 73. This one, 73. Means 73. The what? The piles. The length of this, no? The length. So 14. That is the dimension 14 plus that is the dimension of the HP. Okay, so we have elevation 220 as a reference. Then next below, proposed class 2 RIPrap. So there is a definition of different types of RIPrap. So meaning I am correct that this is a RIPrap. So starting from this point, going down up to this is a RIPrap. There are several types of RIPrap. So this is just class 2. So there is a definition for class 2 RIPrap. So we can confirm it online right now. So that class 2 RIPrap. What do we mean by class 2 RIPrap? That is a definition. Okay. So class 2 RIPraps, okay, may have what? Size 24 inches down to 12. Use erosion control. Okay. So class 2 is about 18 inches to 26 inches. Class 1 is about 12 inches to 18 inches. Okay. Okay. 12 inches to 18 inches, that is the size of the stone. That is the size of the stone. 18 inches to 26 inches, that is the size of the stone. And that is class 2. Class 1 is 12 to 18. Class 2 is 18 to 26. That is what we meant by class 2 riprap. Imagine that. One stone is about 18 to 26 inches. So 26 is more than 2 feet. So that is how big the stone. For big stones, okay. So we can say that maybe that is boulder. I think that is called boulder, or you can review your geotech and find out what is the layman's word for stone with that particular size, 18 inches to 26 inches. So that is a big stones, okay. So that is for riprap, okay. And the dimension for that is 1 inch, okay. 1 foot, 1 foot, and the size of the rock allowed is what? 18 to 26, meaning there are part of the stone that is not pasted with what? With masonry or mortar. There are parts of the stone. About what? 2/3, about 2/3 to 1/2 to about 2/3, 26 over 12. That is less than 1/2. So about 35 or 40%. 40% to 66%. 40 to 66% is covered by what? Paste of cement and water, sand, cement, and water. So that is what we mean by this portion. Okay, so we can analyze if we take a look at the details. Okay, we can analyze it. Okay, existing, there's an existing class 2 riprap, but proposed class 2 riprap. So there's no change between existing and proposed. Meaning existing is the what? Broken lines. Even in real construction, even in building construction, all the existing constructed building is drawn using broken lines, and all the proposed construction is drawn using solid lines. Okay, so I have an experience planning, drawing, and submitting for approval an engineering plan with that what addition or amendment to the initial engineering plan. So I submitted with the existing plan in what? Broken lines, and the proposed plan in solid lines. So that is what we meant by this. Okay, existing, okay. This is the slope of the existing. So it is not what given as the in the drawing, but what is the slope, but there is an existing, okay, riprap with this particular slope. Okay, so and bent just below those we have what? And bent 1. So there are minimum, of course, minimum 2 embeds on opposite sides of the bridge. So this is what we meant by those symbol here. So this symbol means C note on sheet 2 of number 6. Okay, sheet number 2 of 6. So there are 6 pages of engineering plan. So sheet number 2, please look at it for details, additional details of this. Okay, so that is what we mean by this type of symbol. And then this type of symbol here means bottom of end bent cap to top of riprap burn. Okay, so riprap. Okay, so bottom of end bent cap. That is what we mean. So an invent will have a cap. Okay. So normal to the invent. So those are the symbols. So just below that, just below the square box, we have what? We have this specific. This is now the plan view. This is the plan view. Okay. So this is the plan view of what we are looking at. So we have what? Pentable Fayetteville bill. So meaning this is the what? The address. So time. So there is time when they originated, details, date. So yellow. So we have designer and who check this. Highlighted changes. So there's none. So these are the requirement of their building code, of their construction code. Okay, but in our country this is different. So this part is different. So we can just take a look at the details. This part is what we call we have what? We have the reference begin front slope. This one, begin front slope. Station 87 plus 93.21. That is the point corresponding to the above reference point. Okay, so that is the point corresponding to the above. Also this one is the point corresponding to the above point. So the elevation drawing. Okay, so this is the what? Plan view with the exactly the same reference points. This one and this one are the reference point. So those are the reference points. So we can what? Measure it with the grid references 88 and 89 plus 00. So we have what? Connecting these points. Connecting those points. Okay? So we can have what? The correct direction of the bridge. So begin approach slab. So this is the approach slab. We call this as approach slab. And this is the beginning. So this part is the approach slab. Okay. So under this we have the end bend. Below this approach slab. Okay. So we have what? 90 degrees. Okay, 90 degrees from this point to this point, 90 degrees. So again, we are through with this, we are through with this, we are through with this, and then arrow to SR 1415. So there is another reference. He is saying to the left side, to this direction. So specific point. Okay, SR 1415. Here, let us start again at the top. 1 foot 7 inches minimum berm. So similar to the the details at the top view. So 1 foot 0 inch minimum, earth to berm, normal to cap. Okay, berm is an English word. Berm is an English word. So if you don't know that English word, that is an artificial ridge or embankment. Okay, or it means shoveled earth. Okay, that is what we mean by berm. Okay. A berm is a level space, shelf or raised barrier separating areas in a vertical way, okay, especially part way up along slope. So it is a sort of a separation, or you can see it as what? As in a road, for example, you will notice a berm. It looks like a hump. It looks like a small hump. But here, this berm may look like bigger than hump, because we are looking at a project that is very large. This is a very big project. It's a very big bridge. So this berm is maybe looking like that. No? So that is what we mean by berm. If the berm is small, it would look like a hump in the road. Okay, the road humps. Okay, so it means what? It is a hump separates, or the purpose of a hump is to reduce the speed of the of the incoming vehicles, but the berm has a different purpose to what? It is a what? A raised barrier separating areas in a vertical way. So that is the word. Okay. So what else can we see in this figure? So earth berm, normal to cap, again the same as just we had explained at the elevation view. So we have this portion. This means it is what? Where is the riprap? So this is the riprap. This is the proposed riprap. So the existing riprap is this area. So all the what? The broken lines. This is the existing riprap. Okay, so that is the existing riprap. So the riprap is actually not 90 degrees with the direction of the bridge. Okay, this is the center line of the bridge, not the center line. The straight line reference of the bridge direction, and this is 90 degrees to that. This is 90 degrees. However, the riprap is not in perpendicular to that, or this riprap going down riprap. This is the going down riprap. This point is actually on the same elevation as this point. This point, the same elevation as that point. So if you can imagine that these points are of the same elevation, this riprap is actually going down. So this is going down. So this proposed riprap from this portion going there is actually going also downward. Okay. So next we can what? Oh, again, this is proposed RIPrap plus 2. Okay, this okay. We already explained. So next we have what? 90 degrees. We already explained. Next we have shoulder. What is what we mean by shoulder? SHLDR, shoulder. 5.906 feet. Okay? So 5.9 feet, almost 6 feet, is the size of the shoulder. Meaning from this point to this point, 6 feet. So in 6 feet, what? A small car or a tricycle could be able to what, pass through it. However, it is shoulder for what? Emergency stopping. No? So this is shoulder. On the other side, the shoulder is a little bit wider because 5.939. This shoulder here is 5.906. 5.939. So a little bit. It's not very substantial, a little bit different from each other. Anyway, those are the shoulders. So from or between these shoulders, we have what? 3 at 11.811 feet. Okay? So meaning, we have what? If you can measure this point to this point, we have to multiply. That is what? That is 34 something, no? 30. So 3 times 8 is 24. So 3, so 35. About 35.4 something, okay? About 35.43 feet. So that is the what? 35.4 feet is for 3 lanes. Okay, so 3 lanes. So one car is really about 11.811 feet. So that is the lane width. Okay, so take note of that because we will compare that in our own country. How much the size of one lane in our own country. Okay, so if our local code, local standard uses those international standards, we will have the same. We'll have the same size for lanes, okay, for car lanes. So here, earth berm, normal to cap, again, same as the above. So from this point to that point, that is all what? Berm, normal to cap, earth berm, okay. Those are what? The necessary use of soil actually. So it is a berm. So next we should proceed here. Next to it. So it is still the top view. So let's try to go to the right side. So we have what? We have the north 77 degrees, 1 minute and 60 seconds. 77 degrees, 1 minute, 60 seconds. That is the direction. The Earth's direction with respect to the globe. Okay, so we have what? North to northeast. That is a northeast direction. So the reference is north, then measure 77 degrees, 1 minute 60 seconds, going east. I am very much worried about this. 77 degrees, 1 minute 60 seconds. Can anyone confirm that I am reading the plan correctly? Is that correct? Is that this one? Just below my picture. Just below my picture. Here. Just below the one. North 77 degrees, 1 minute, 60 seconds. Is that correct? Okay. Can anyone confirm? Okay. Because a 77 degrees, 1 minute, 60 seconds. So, according to Tabes, Roleo, okay, they confirm. However, what can you say about 60 minutes? 60 seconds? 60 seconds is 1 minute. So, why write it like 60 seconds when 60 seconds is 1 minute? So, isn't it better to write it 77 degrees, 2 minutes, and 0 seconds? Okay? Okay. Do you understand? Do you understand that 60 seconds is 1 minute? So, therefore, it is better to write it as 77 degrees, 2 minutes, and 0 seconds. So, I don't know. I am not a geodetic engineer. So, maybe there is a rule, there is a code. Maybe there's a code in geodetic engineering. I don't know. I am not aware. This is the first time. This is the first time So, we can learn something. Even I am learning. No? I will what? I will, so, you can help me figure out later as your assignment. Let us research if we can specify it as 77 degrees 2 minutes, or it is a must. Is it a must that we should show it as 77 1 minute and 60 seconds? Oh, that is our assignment. That's a good learning. Okay. Okay. So it's in every little detail we can take out an important information. Okay. So this one is the top view of our one. This is the column. Okay, column. This is the location of the column. So we have what? This particular portion is the what? The specific point station 89 plus 23.34. So according to the direction. So drawing and a straight line with this direction 77 degrees 2 minutes, connecting those points, we can have what? A straight line drawing. And now we can place the what? Column. We can place the important structure with that reference points. Okay? So that is the importance of that reference point. Okay? So span A. So this is the first span. From this point to this point. That is the span. And we call that span A. How much is that? 118 feet, 0 inches. Okay? So that is the span. 118 feet, 0 inches. So that is a very long span. 118. So if you try to convert that to what? Convert that. Let's convert that to meters. 118 is actually equal to, use your calculator, that is equal to about 36 meters. Imagine that, 36 meters. 36 meters is about four residential house. Okay? 4 houses. So that is the span of what? Of column to column or support to support. This is the support and another support. So if we can say that the support is simple support, simple beam. So this is our reference points. So from this point to this point, that is our simple support. Okay? So that you can just what? Subtract the station amount, no? So 89 plus 23.34. Then here, okay, let's go back then. So 118 is about 36 meters. Imagine that span. Okay? Imagine that when we are able to previously show a video, the viral one, or in 18 meters of building span was what? Was damaged. Okay? It fell down. Just damaged. That is only 18 meters. This is 36 meters. Imagine that. Times 2. That is exactly double. No? About double. So we have this bent one control line. Okay. Bent control line here. So there is a what? An structure that connects one column to the other. So we call this as what? Multiple column structure. So there are two types, multiple column and single column structure. Okay. So let us proceed to the what? Let us proceed downward first. Let's proceed downward. So going down, we have what? Total length of bridge 751 feet. Imagine the length of the total length of the bridge 751. So that means 751 in meters. 751, that is 229 meters. Imagine that, 229 meters. Imagine 100 meters, very long because of what? We have 100 meter dash. 100 meter dash is very long. No? And this is 229 meters. Imagine that. The total length of the bridge, of this bridge. Okay, so we are on the lower end of the plan, so let us go to the right side. Let us go to the right side of the plan. So span B, and you can see span C. So when you see a symbol like this, it means there are still so much connected here. Okay? And sometimes we are using the symbol because those parts that are connected here are just what? Are just the same as those parts that are here. The details are just the same. So that's why we are just using the symbol, because those connected details here are just similar to this detail. So therefore, typical. We have the typical dimension, typical detail. So we just use that symbol. This one, this symbol, specific symbol. So we can see what is span C and span B. So there are different dimension for span. So the span A is 118. Span B is 132 and 6 inches. Span C is 170. Okay. So therefore, we have different span. Okay. Length, different span length. That is quite normal in a bridge because we have portions that we want to avoid. That's why. And even in buildings, when there are portions that you need to avoid, so you will have what? Different column to column distances. But usually we want column to column distances to be the same. If possible. Okay. So let us go here. Creek. Did you see the creek? Creek, Beaver Creek. So this is the name of the creek. So we have the creek. So can you see the creek? Oh, Beaver Creek. That is the creek. Okay. So bend control line. So 90 degrees again, typical. So the bend control line. So this is the line which is 90 degrees with this reference line. Okay, so okay, you cannot see the reference line. Yeah, you can see it, but we have what? Temporary work, bridge, see environmental permit plans and special provision. So there are temporary work to be done. So this portion, this broken lines, temporary. Okay, for temporary work. Okay. So again, let us go back to the top. So as you can see, we have what? The elevation view. So now we are on the what? 90 plus 00 and 91 plus 00. That is our reference grid now. And we are span B and span C. So span B, we have what? WS. So that is our water surface elevation. WS meaning water surface elevation. That is the height of the water. 194.13. So that is the surface of water. So you will see, sir, water surface will have a different elevation at different time. Morning, the different water surface elevation. Evening, lunchtime, the water surface elevation changes. That's why in this particular engineering plan, we have the what? The time. It is written on the plan. What is the time? Can we back up? Here, time. We have time. This is AM. Okay. This is about what? 6:34 minutes and 32 seconds AM. That's why it is included on the plan because we have what? The elevation of the water surface. Okay. So let's go back to that area. So and then we have another elevation 206.79. Okay, so this is the upper elevation, lower elevation of the water surface. Okay, so we have what? The minimum and maximum measured water surface. Okay, during the inspection, during the visit, during the inspection and visit. Okay, at different point in time. So there must be two different times. Okay, this cannot be measured at one single time, of course. Okay, so there are at least minimum of two visits. Okay, and they will record the time up to seconds. The time is recorded. Okay, so elevation here of the natural soil surface of the bottom of the existing ground line. So this is the existing ground line. So this broken line, as you can see, the footings is above. Take note, right now, usually the footing is below the ground. The footing is actually above the ground here. Okay. Take note, this portion is what? Bottom of the footings. Take note, this is the bottom of the footing and this is what? Existing ground line. Existing ground level is what? At elevation 187.3 plus minus. Okay? This is the elevation of minimum water level. So at minimum water level, we can actually see the bottom of the footings. Visually, we can visually see because this one is what? 194. Okay? The bottom of the footing is 190. Sorry, we cannot see because 194 is higher than 190. So, about 4, no? We cannot see the bottom of the footings. But the ground is really 187. The bottom of the footings is 190. So, there is what? About 3 feet. Can you imagine that? About 3 feet. 3 feet is about 1 meter. No? About 3 feet. So 900 mm. So 915 mm. That is 3 feet. From this ground level to the bottom of the footings. So then piles. These are the piles that we are talking about. That is the HP 14. So this is by, not plus. So 14 by 73. Okay? So meaning 14 is the dimension of the HP steel piles. 73 is the, I think 73 is the length. So I will confirm back from my previous search. So H pile 73 means width. 73 is the same as W shape. The same as W shape. 73 meaning 73 pounds per foot. That is what we mean by 73. So that is not plus. A while ago, we thought that the correct reading is HP 14 plus 73. The correct reading is HP 14 by 73. I just confirmed that 73 pounds per foot. So 14 is the dimension. That is the width. Okay? The width of the of the flange. That is the width of the flange, 14. Okay? And also, the height is also 14. So, plus minus, it is not exactly 14. It is not exactly width of 14. It's not exactly width of height of 14. But it is about 14 by 14. The height of the web is about 14. The width of the flange is about 14. So that is what I meant by dimension of this. Okay. So let us move to the right side. Moving to the right side. Span C and D. Similar. So similar to previous span, of course. Again, so we see a higher elevation here, 188, because the neighboring elevation is 187, so this is lower. So this is going to be higher, so going up. Okay, going up. So this is the lower portion, maybe the lowest portion. Okay. So, and also we have the arrow. This arrow means the north. This arrow direction is north. Okay. This is north. And this arrow is very important, particularly in roads and highway. The north. Okay, this arrow. This engineering plan would not be complete without this simple arrow. This is not actually simple. Okay, it is very specific, must be surveyed. Okay, and actually take note of the 77 degrees, 1 minute 60 seconds. So the measurement is up to seconds. Okay, so that is what we mean by this. So anyway, we have what? What? Cumberland County. So this is what? The name of the Cumberland County is what we have in our local dialect as barangay. So it looks like it is a barangay in our country. County. It is a barangay. Okay. And then the what? The Department of Transportation. So in our country, we call it as DPWH, Department of Public Works and Highway. So state of North Carolina. North Carolina is a state in the US. So general drawing, bridge over Beaver Creek. So Beaver Creek is the name of the river, okay, or the water, body of water. Okay. So freeway, the name of the freeway. Fayetteville Outer Loop is the name of the area. Okay. So between SR, so I think this is a major road name. So something road name 1415 and NC 24. These are name of the roads. Okay. So I think this is North Carolina Road 24. I think something like that. Okay. So those are what we mean. So any question about the details in this particular page? Any question? Let's go to the next. Let's go to the next. So this is now the what? Typical section. We have now in the typical section. So we will try to enlarge again. Let's try to enlarge. Enlarge it further. So it is now 150% enlarged. Okay, 150 enlarged. Is it okay? Let's see. Let's try. Let's try 150%. Not yet. Can you see it? Can you see it? 150%. Let's try to enlarge it further. 2 clicks. Okay, so 170%. So that we can what? Analyze. We can see all the details. What are the types of details that we can expect? Okay. So now, since we have the a good understanding of the location, the positions of the column, position of the starting point of the bridge, and the span, and even the total direction, the major direction of the bridge. So we can now what? Proceed even faster now. So we have on the top what? 50 feet 6 inches. Okay, out to out. So out to out. So meaning we are what? Actually looking at the section. Okay, cross section. This is cross section. Okay, so this is cross section. Out meaning the extreme. The farthest extreme on left side to the farthest extreme on the right side. That is what we mean by out to out. Okay, so the dimension is 50 feet. So this is a very wide. It is a very wide bridge. Okay, so there are actually what? 3 lanes. There are 3 lanes of this bridge, as we saw in the top view. So 3 lanes. So we have to expect 3 lanes. So 50. So we have what? 11 point something, no? So 11 point, I think 11.4 times 3. That is the total lane plus 6 or 5. Okay, 5 feet. 5 feet on each side. So plus the what? Plus the edge. So I think it is about correct, about 50. So the estimate is, my estimate is about 50, and that is about the correct size. No? 50 is the exact 50 feet and 6 inches. So next we have what? Clear roadway. How much is the clear roadway? This is 47 feet and 3 inches. So clear roadway, that is what? Starting from the end of the parapet, okay? End of the concrete barrier or parapet, no? Concrete barrier. End of the concrete barrier to the opposite concrete barrier, okay? That is our clear roadway. Okay, take note of the technical term. Technical term. Clear roadway doesn't mean you will you will exclude the what? This emergency shoulder. So include the shoulder, the total is 47. So 50 minus 47, that is 3 feet. And divide by 2 because 3 feet is total. So one side is 1.5 feet and the other side is 1.5 feet. That is what we meant by that. That's why you can see here 1 feet 6 inches is actually exactly 1.5 feet. As you can see here, 1 feet 6 inches. Oh, as you can see here, 1.5 feet. 1.5 and 1.5 to the other. So the total is here 1 feet and 6 inches. So 1 feet and 6 inches plus 1 feet and 6 inches. So that is 3 feet. So 3 feet plus 47 feet. So 50 feet and 3 inches. This is 6 inches. So 6 inches minus 3 inches, 3 inches. Divide 2. So 1.5 inches here, 1.5 inches to the other side. What is that 1.5 inches? So the concrete barrier is what? Set back at 1.5 inches. Okay, so there is a very small setback, 1.5 inches. So the parapet or the concrete barrier here, there is a 1.5 inches setback, then 1.5 feet dimension of the concrete barrier, then the clear roadway. So exactly our computation here. So we are correct in that analysis. Okay. So next. So from this point to this point, we have 17 feet and 9 inches. So to this point. So this is the grade point. Okay. Grade point. Okay. So grade point, that is the reference point of the what? The wearing surface. Okay. So please give me a benefit of the doubt with that. If the grade point is below the wearing surface or on top of the wearing surface. Okay. So please give me the benefit of the doubt. So here we have only what we call grade point. Okay. So grade point. This is the line for column 1. Okay. So meaning just below this we have the column. That is what we mean, no? Below this. So we have the column here. So meaning we have what? Here are the steel plate for the what? For the support, and therefore that is what? The column cap or the pier cap. We have a pier cap here going this way to support these steel plates, and then the pier is actually directly on this line. Okay? And on the other side, it is also the same. Same on the other side. So we have what? 34. What is this? 34. Cannot draw. 34 something. 34. What is this? Can you read this? 34 something. Let us enlarge it further. So enlarge by 2 clicks. So 3 clicks. So we have what? Times 2. 200%. We have now the 200%. So I think we can now read the details. Okay. So we have what? 34. 34 something. 34 minus something, and then 8 inches bars. Okay, so this is what 6 inches typical. Okay, 6 inches typical here. So the what? The first, okay, take note of that, 6 inches. The first introduction of reinforcement. As you can see, can you see the dots, the first two dots? The first two dots here, this one and that one. These first two dots, 6 inches typical from the edge of this pavement. So the edge of the pavement of this bridge, from the edge of the bridge, we have 6 inches. Then we introduce reinforcement. That black dots, 1 and 2. We use 2 dots, okay? And then that is what we mean by bars, okay? So number 8, or is that number 8 or number 4? Number 4 or number 8? Eight inches bars. So 34. So I cannot read it. That is top of the slab, no? So top of the slab. So on the top of the slab, we have that reinforcement. I still cannot read it. Can anyone read? Can anyone read that details here? That is very important in our reinforcement. So we have what? Next to it is 33 spacing. ISPA meaning spacing. 33 spacing at 1 foot 6 inches. Okay? So 1 foot 6 inches, so times 33, that is equal to 49. That is what we mean by that. So we can use our calculator. Use your calculator. Okay. So enter 1.5. That is 1 foot and 6 inches. That means 1.5. Multiply by 33. Multiply by 33. That is equal to 49. 49.5 meaning 49 feet and 6 inches. That is exactly. So meaning to say that is what we meant by that number. So meaning there are 33 of this reinforcement is spaced at 1 foot 6 inches. So there are 33 of them. Okay? 33 spaces. So there are 33 with the spacing of 1 foot and 6 inches. So therefore the total length is 49 feet and 6 inches. Starting from this couple of reinforcing bars. So that is what we mean by this. Okay? So okay. If we say top of the slab, we are just looking at the reinforcement at the top. Okay? So we are just looking at the reinforcement at the top. Okay? As you can see, the reinforcement at the top is different from the reinforcement at the bottom. So top, middle. So I think there is, where is the bottom? So there are bottom bars here, but actually I think this is top and bottom. Okay. Okay. And then we have what? Is this K bars? Typical over X of girders, no? Okay. So girders. So we have girder beams. Okay. So 2, 5. So 2, number 5. So I think this is I cannot read it, but I think this is number 5. 2, number 5. This is 34, number 4. Okay, so that is 34, number 4. This is 2, number 5. This is K bars. Okay, K bars. This is B bars. I think this is B bars. This is 34, number 4. Okay, so this is top of the slab. This is over extend girders. Okay, so specifically the lower portion here. So there are two lines. So there are two lines of reinforcement here on top and below this black dots. Okay, there are black dots near the surface, near the top surface of the bridge. Okay, there are series of black dots here, and over that black dots we have reinforcement. There is a drawing of lines. That line is reinforcement, and under the same dots we have also reinforcement. Okay, so there are reinforcement on top of the black dots and below the black dots. Okay, so those are lines of reinforcement actually. Okay, and this is one details of that. So 2, number 5. So what is the dimension of number 5? We have a table. What is the diameter of number 5 reinforcing bars? Okay, so we have a table for that. So please look it up. What is the diameter of number 5 bars? That is what we mean by this. There are 2 of them. So meaning, if there are 2 of them, it only means that the bars above and below this series of black dots are the same. They are the same. They are both number 5 reinforcing bars. Okay, that is what we mean by this. Okay, so next again we have the concrete barrier rail, typical. Then next below it, construction joint. So this is our construction joint. The the broken lines construction joint. Okay, what we mean by construction joint? They are touching each other. They may be touching each other, but they are not physically a single unit. So meaning it can be what? It can be moved. Okay, they are not a single unit. This concrete barrier and this one. Okay, they are poured separately. Okay, that is what we mean, because we have what? Joint. We have construction joint. Okay, so maybe there are several what? There are several locations here wherein you can use pipe so that water inside this bridge will move down. Okay, will fall from this side. Maybe you can have a pipe going here for your what? Water downspout. Okay, you can have a water downspout here like that. Okay, okay. So now next we have 2 3/4 beam bolster upper at 3 feet 0 inches CTS. Okay, so we have a detail. So we have a details on other parts of the engineering plan. We will look it up on that specific plan. So that is the beam bolster. Okay, so we'll look it up on the right page of the engineering plan later. Okay, next is 2 inches. Okay, So we have 2 and 3/4 beam bolster here. But now we have what? 2 inches high beam bolster. So again, beam bolster here. Okay. So at what dimension? What is the dimension of that beam bolster? 4 feet. At 4 feet, 0 inches CTS. Okay. So center to center distance, 4 feet. Here, center to center distance is 3 feet. Okay. So they are both beam bolster. So this is high beam bolster. So this one. This one. This one. This one. So this black triangular part. Okay. This black triangular part, those are high beam bolster. Okay. Now to number 5. What is this? K bars, typical over int girders. So this is another location for girder. Okay. So this is another location for girder. So this is X girder. This is int girders. Okay. So int girders, X girder. Okay. So bolster. Okay. So grade point. This is the same grade point that we already talked about. So we have here C details. So we will see the details of this later on. This connection, how this is connected. What are the important details here? So we will see. This is the same with this. So this details, same with this details. Okay. So again here, there are two, number 5, reinforcing bars. Okay, so 1 and 2. Okay, so 1 and 2. So this is the flange. This is the flange of the int girders. This is the flange of the X girder. Okay, this is the flange of the same girder, the X girder, lower flange. This is the lower flange of the int girders. This is the lower flange of the int girders. Upper flange of the int girders. Okay, so we will see the details of that. Can you see the description at the box? So we cannot because of the live picture. Let us try to move it downward. Okay, so we moved it downward, so we can now read the contents at the box, inside the box. Use 2 1/2 inches high beam bolster. So we have that legend, so that is the same legend. So 2.5 high beam bolster, no? But here we have what? 2 3/4. This is not 2 1/2. This is 2 3/4. Upper, so BBU at 3 feet 0 inches centers in areas of slab with number 6 top. Okay, number 6 top 8 inches bars. Okay, so I don't know if this is 8 or B. I cannot read if this is 8 or B. So number 6 top 8 bars. Okay. So meaning we need number 6. Okay. So we can. So this is number 6. This is number what? Number 5. This is number. So number 6 bars are bigger than number 5 bars and number 4 bars. Okay. So this is number 6 bars. Number 5 bars. Number 5 bars. So in this area, number 5 bars. This one and this one. So here and here. But here we are going to use this one, number 6, top bars. Okay. So top bars, this line. These lines are the top bars. Bottom bars, these lines are the bottom bars. Okay. Next, girder. So we have girder number 3. So we have one X girder is number 1, int girders number 2, another int girders, girder number 3. CL meaning center line. This is the center line of girder number 3. Girder to the next girder distance, this is what? 4 feet 10 and a half inches, 5 feet 10 and a half inches. You can add so that you can determine the total girder to girder distance. That is what? 5 plus 4 is 9 feet. 10 plus 10 is 20. So 1 half, so 21. So 21 minus 12 is what? 9. So therefore 10 feet and 9 inches. So this distance is 10 feet and 9 inches. And that is exactly here. 10 feet and 9 inches. That is exactly here. So there are 4 spaces with 10 feet and 9 inches. So if you multiply, that is 43. 43 feet. That is exactly 43 feet. So 4 times 10 is 40. 4 times 9 is 36. 36 is equal to 3 feet. So that's why it is 43 feet. So exactly what we conclude. Okay? So there are 4 times of this. Okay? 4 instances of this. Okay? From what? From this point? From this point, 1 and 2. We are at the middle. We are at the middle. So another 2 so that we can make up the 4 spaces. Okay? So this is what? 3 feet and 9 inches from the edge to the first girder. Okay, so any question? Any question? So next. So we have the 4th space and the total must be what? 43 feet. 4th space. So this space is 1 foot. 1 foot from this to this point. So that is the location of what? This is the center of girder. This is what? This is the what is this? This is pointing to what? This is pointing to this part. This is actually the rib. Okay, so we have what? Metal stay in place form. So it could be what? It could be decking form. So decking form could stay in place or the decking could be pulled out after the concrete dries. Okay, after the concrete dries, the decking form works, meaning form works. Okay, so there are decking form works and that could stay in place like this. So the metal will stay in place. Form. So this is the form work. Okay, it is a form work which is what? Defined as temporary. A form work is defined as temporary, but it is stay in place. So it will not be temporary. It is permanent because it will stay in. will stay in place. So that is the edge of the formwork. So there is a formwork like that. So that is from the center of the girder, that is 1 foot. Okay? At the dimension of the formwork. Okay, so details A, we will see that later. So we have what? 2.5 clearance. So 2.5 clearance here. So meaning the concrete cover at the top is 2.5. So that is about what? 40 mm. So we are using 40 mm in our country as a concrete cover. So these are specific dimension. You can memorize that 40 mm for concrete cover. That is specific dimension. That is not guesswork. That is not guess. That is specified and planned. Okay, so 40 mm top concrete cover. So we have this dimension 1 and 1/4 inch concrete cover at the bottom. So at the top we have 40 mm concrete cover. This is not 40. 2 is 50 and 1/2 is 12. So 62. 62 mm. You can memorize that. 1 and 1/4, this is what? 25 plus 6, 30. So about 31. So 31 at the bottom. Bottom concrete cover is 31. At the top is 62. Okay? So it doubles, no? Double. Okay? So number 5, A bars. So I can read it now. A bars meaning what we read a while ago are B bars because there is A bars. There is A bars, so there is B bars. Okay, so number 5 B bars and number 5 A bars. Okay, so we have this number 5. Okay, so we have a definition of what we mean by A bars. Okay, so this is B bars. As you can see, this number 6 top B bars. This is B bars. Okay. We will look at the definition later. Okay. Maybe at the bottom of this page. So we have again the barrier, the concrete barrier. Okay. So typical height of the barrier 3 feet 6 inches. 3.5. Okay, 3.5. So 3 feet and 1.5. So this is about what? This is more than 1 meter in height. About 1 meter in height. So if you divide 3.5, so this is actually more than 1 meter. So this is 1.07. So meters. Okay. So 1.07. So 1 meter and 70 mm. That is the measurement. So 7 inches, 7 centimeters. So 1 meter and 7 centimeters. Okay, so that is about 1 meter. My estimate here before is 1 meter. So I think in our country, this is 1 meter. I think. So let's confirm later. So we have the beam booster here. Okay, the white triangle shape. Okay, so a beam booster here is what? Black triangle here. a black triangle, a beam booster. Take note, we are looking at totally small details. Okay? We are going to become a civil engineer. We will look at the very small detail. The smallest details we should be able to know. Okay? So you have to rewatch, repeat and repeat watching this video. So we have what's next? So 1-in-1 port high beam booster upper. Okay. So a BBU at 4 feet center. See notes. So we will see the notes later. So the same here. We already know about this line. We already know about this 1 foot and 1 foot on the other side. So that means the start of what? It is here. It is referring to the reinforcement bar. But here, I think there is a mistake in the line. Okay, that's why it is referring to the metal stay in place form. This is supposed to, the line is supposed to go farther up to this, what? The end of the lower reinforcement bars. Oh, the end of the lower reinforcement bar. Notice that there is no reinforcement bar at the bottom. Okay? Exactly on the what? On the or above the girder. There is no reinforcement at the bottom. Okay? The reinforcement is at the top. When we are at the, take note of this. Take note of this. We have the principle of reinforced concrete. I will talk about this. Okay? That's why please remember this. At the point wherein the concrete is directly above the girder, there is no bottom reinforcement. There are top reinforcement, but there is no bottom reinforcement. Take note about that. Take note about that. Okay? Please remember this. Okay? We will talk about that on maybe next week, next meeting, because our topic would become what? Doubly reinforced concrete. Doubly reinforced beam. So, that is what we mean by doubly reinforced. Okay? Oh, again, here, there is no lower or bottom reinforcement directly above the girder. So, every girder, there is no bottom reinforcement. And then we will look at the details. Detail A. Okay? So, next information here. 9 inches. Okay? So, that also involves the location of the reinforcement. That involves the location of the, meaning placing all the reinforcement. Okay? During the construction, there are measurement of that reinforcing bars. Okay? It should be measured. Okay? It is not what? A guesswork. They are not guessing. Okay? And if you see, there are some of you who are actually working in the construction. Okay? There are very small number of project in charge that would measure that in actual. They will not measure that in actual, and that is supposed to be measured by the project in charge. The reinforcing bar to the next reinforcing bar. Okay? That is supposed to be measured. Okay? It is always, even this one, in this plan is international caliber expert engineers. Okay? This is in the United States. Look, in the United States, they are being sued in court, unlike in our country. Okay? In our country, the engineers would just say sorry, and that's the end of it. In United States, they will be sued for damages, and they will call for the revocation of their license. That's why these engineers are expert. Okay, and that's why these plans must be followed. In our country, there are no inspector or checker that would measure. Okay, they will look at the plan. They will stay there for 1 hour. The inspector will stay there for 1 hour and converse with the foreman, converse with the site engineer, and then that's all. He will sign the inspection certificate. That's all. Take note. If you become an engineer and I am your consultant, you will see. If I am your consultant and you become a civil engineer, I will look after you. Okay? Okay? I will measure everything and you will see. That's why I'm telling you. I'm telling you right now. So please listen. Please listen. These are not a play. We are not playing. We are serious about it. These are the things that we need to understand and implement. Implement it. Use it. Use it in actual. That's why we are making it so serious in this understanding. Okay? So next, what do you mean by this? Okay? Bars at 7.5 inches centers, meaning center to center, typical in bottom of each overhang. So what do we mean by overhang? Overhang means after the exterior girder. This is the exterior girder. Girder number 5 is exterior girder. So there are two exterior girders, girder number 1 and girder number 5. They are exterior girders. So after the exterior girder, we have the overhang. This is what we call overhang. So from this end of the plans, we have the overhang. How many bars? Okay, 7.5 inches, center to center. Okay, from this point to this point. Okay, so 7.5 inches, center to center. At the bottom, so meaning 1, 2, 3, 4, 5. This 5. Okay, these are what we meant by the 2, 3, 4, 5. So there are 4 spaces and 5. So 4 times what? 7.5 inches. Okay, so that is what we mean by. So if you multiply 4 times 7.5, 7.5 times 7.5, that is 15. 15 times 2 is 30. So that is about 30. Okay. Okay, so in the bottom or each, meaning on the other side, it is also the same. That is what we mean by this. Okay. Any question so far? So here, what do we mean by this? This is the last information. 15 of number 5 B bars. Okay, 15 of number 5 B bars at 7.5 centers. Bottom of slab. Okay, this is a typical bay. From this point to this point. So from this point to this point, bottom of slab. This is the bottom of the slab. Take note. This is the bottom of the slab. This is the top of the slab. So A bars, take note of the A bars. Those are the A bars. This is B bars. So now I fully understand what we mean by A bars and B bars. B bars is the cross bars, looking like this. And A bars, B bars are going right there. No? And A bars is there. No? So they are 90 degrees with each other. So A bars, in your monitor, look at your screen. A bars are going here and B bars are going there. So they are 90 degrees from each other. That is the full information we got from this plan. Okay? So now, complement our drawing with specification and notes. Oh, here, notes. Okay, we will go faster so that we can complete the notes. Okay, at least at this fifth slide. Okay, notes. Provide 1 1/4 high beam bolster upper. Okay, that is BBU. Okay, beam bolster upper. That is what we mean by BBU. B meaning beam. Another B bolster. U upper BBU. Okay, so at 4 feet 0 inches centers at top the metal, stay in place forms to support the bottom mat of A bars. Okay, so what we mean by mat? So there are several reinforcing bars. So if you are placing the bars during the start of the construction, placing the bars one after another, that is actually we call matting of the steel bars. Okay, that is what we mean by bottom mat, okay, of A bars. So there are two locations of A bars, bottom and top. Okay, a clear distance of what, 2.5 above the top of the removable form. Okay, so we already explain this on the drawing itself. So this is for clarity. This is for clarity. So we saw this on the drawing and we confirmed it in the notes. Next note, set top of the expansion joint, seal device. So there is a sealing of the expansion joint. Okay? A minimum of 1/8 inch, okay, and a maximum of 1/4 inch below the top of slab. Therefore, the expansion joint is actually located near the edge of the bridge where the concrete barrier is located. That is one location of expansion joint. Okay, we already seen those joints on the drawing, but now there is an additional detail. The detail is 1/8 inch and 1/4 inch minimum and maximum. Okay, cleared. We are cleared about those things. So next, metal stay in place forms shall not be welded to beam or girder flange. They don't weld it to the girder flange in the zones required RIPbE V-nuts test. What do you mean by RIPbE V-nuts test? Take note, RIPbE V-nuts test. This test is for hardness test. No? So see girder detail sheet. Okay. So there is an instruction that the forms, the metal forms, must not be welded to either the girder or the beam. Okay. Next, barrier rails in a continuous unit shall not be cast until all slab concrete in that unit has been cast and has reached a minimum compressive strength of 3,000 psi. So we can now relate about this. Okay. Yesterday we talked about problem solving, and one of the given data is 4,000 psi. That is what? FC prime. That is what we mean by FC prime. This is FC prime. This is the reason why on-site engineers are making up cylindrical test specimen. And those test specimen, do you know why? Do you know what they are doing on those test specimen? After drying, those test specimen, cylindrical specimen, will be put inside the water and the drum with water. Put those test specimen in the drum with water. Then, afterwards, after several number of days, bring it to the laboratory site for testing. Okay? And then, they will give you the compressive strength number. So, here, the minimum is 3,000. What did I tell you? This amount is 3,000 to 4,000 in our country. That is the typical amount. Okay? Next, previously cast concrete in a continuous unit shall have attained a minimum compressive strength of 3,000 psi before additional concrete is cast in the unit. Take note. Okay? So, when we are what? Pouring concrete, okay? What? It's better to pour at once, at the same time. Okay? But that is impossible. There are times that we stop and then proceed or resume another time. So, the unit shall have attained a minimum compressive strength of 3,000 before additional concrete is cast in the unit. Wait, you have to wait. And how much you have to wait? You have to test it to become. That's why the project in charge would make several cylindrical test specimens. Not only 3. The minimum is 3, but it will make so many, about 20, 50 cylindrical test specimen. Because of this. Okay? Take note. Those are the real job that you will see on the construction site. Okay? Next, structural steel erection in a continuous unit shall be complete before false work or forms are placed on the unit. Okay? So, we have to be prepared. We prepare the support. Forms and false work are support, but we need to support the support. Okay? So, before steel erection, the continuous unit, okay, shall be complete before false work or forms are placed on the unit. Okay? So we have what? We have the preparation. Next, what is this? Number 5, G. Number 5 gauge bar. So that is what we mean by number 5 gauge bar. May be shifted slightly as necessary to clear reinforcing steel. Okay, so number 5G. Okay, so number 5G is smaller than number 6. So, number 5 and number 6 are the most common size of reinforcing bars used in this bridge. So, number 5 may be shifted slightly. Okay, do you know what we mean by shifted slightly? Okay, so it is what? Number 5. So when some of the reinforcing steel bars will pass through and actually cannot pass through because of some number 5 gauge bar is obstructing the reinforcing steel bars, so it may be shifted slightly like this. Can you see? Can you see this? Shifted slightly. Instead, it is an obstacle. So shift it slightly. Okay? So that is what we mean by shifted slightly. Okay? So the other reinforcing bar cannot pass through. The other reinforcing bar cannot pass through. Cannot pass through. The reinforcing bar cannot pass through. Okay? So shift it slightly like this so that the reinforcing bar can pass through. Okay? That is what we mean by that. Okay? Next, the contractor may, when necessary, propose a scheme for avoiding interference between metal stay in place forms and beam girders, stiffeners, or connector plates. The proposal shall be indicated as appropriate on either the steel working drawings or the metal stay in place form working drawings. Okay, so this is not applicable in our country. The contractor and the The contractor and the project in charge will do what they want. Then just request the design engineer for approval. Okay? They will just request the design engineer for approval. That is what is always being done in our country. Okay? Instead, the correct way, the contractor must request beforehand. That is what I'm telling you. This is again what? The matter of courtesy in our culture. In Filipino culture, we are not courteous enough. Okay? There is no courtesy. They will just do it. Okay? They will just do it. They will just go inside your house and eat your food inside your refrigerator. That is exactly what we mean by courtesy. Okay? Without telling you anything. That is what we mean by that. Okay? The contractor shall adjust girder build-ups as necessary to incorporate a maximum permissible variation in path bearing. So what do you mean by path bearing? Path bearing is one type of bearing. So we are given how many types of bearing? So there are 5 types of bearing in this series of lecture. Okay? So path is one type of bearing. Depth of how much? 1/2 inch. So that is the depth of permissible variation. See path bearing detail sheets. So, okay, allowance. There is an allowance. Okay? For deck drain and connector details, see sheet number 2 of 2. Okay? So maybe last portion in this page, detail A. So after this detail A, we can go. So let us just finish this page. This is the last portion. Detail A. Take a look at the detail A. Detail A. So this is the upper flange of the girder. So this is the upper flange of the girder. So this is the dimension from this point to this point. That is what? 1 foot and 3/4 inch of top of slab to bottom of top flange. What is the bottom of top flange? This is the top flange. The bottom of that is this side. This is the bottom side. This is the top side of the top flange. Okay? Top side of the top flange. This is the bottom of the top flange. Okay? So from this point to that point, that is 1 foot and 3/4 inch. Okay? At center line. Okay? That is center line. Okay? So this is the center line. Okay? Then from that point to this reference line, 3.5 inch build up at center line. Okay, 3.5 build up. So there is a 3.5 build up here. Okay, then what is this? This is the end of the flange. This is the start of stay in place formwork. Okay, metal stay in place formwork. This is the metal stay in place formwork. So one to the other side and one to the other side. Okay. Okay. And if you look up from the lower portion of the bridge, looking up the bridge, this formwork is actually looking like what? Corrugated sheet. It looks like a corrugated sheet. Okay? This portion. Okay? This is the drawing of that corrugation. Okay? Okay, so here, from this reference line to that is 9 1/4 uniform slab. That is now the uniform slab, meaning this upper part of the formwork up to that part. That is the uniform slab. Okay? Any questions? So we are through with all of this. And this is what? Superstructure typical section. That is the superstructure. So including what? The bearing. So bearing is part of a superstructure. Okay? So all of those things, we have finished up to the PIP. I think that is the port. That is only the port slide. Okay, that is only the second page. That is only the second page of our plan. So let us continue next meeting. So this is the sign and seal of the engineer. The sign and seal of the engineer. Here is what? Dominic A. Coletti. So that is his name. Dominic A. Coletti. North Carolina. Professional engineer. So all of the engineers are called professional engineer. Even if they are civil engineer, they call themselves as professional engineer according to their law. Mechanical engineer also called professional engineer. Electrical engineer also called professional engineer. Everybody is professional engineer. All types of engineers. In our country, we have what? Civil engineer, mechanical engineer. I am talking about the license. The license of civil engineer is called professional engineer. The license of mechanical engineer is called professional engineer. All of the license is called professional engineer. That is the license. They can call themselves a civil engineer, but that is not indicated in the license. The license is only called professional engineer. Unlike in our country, we have license for different engineering fields. Okay? Any question? Any question? I will give you 30 seconds for question. If there is no question, we will call it today. So I will wait for 30 seconds. So your 30 seconds starts now. So we can have a more lengthy discussion next meeting, or if ever you have what? If ever you have a specific question, I'm happy to answer your question. So Family Hayes. So there is somebody named Family Hayes. Wristwatch, check, CP, ICE. So meaning, check your clock and look at your cell phone. Okay. And then what? Point and clap 100%. So that is what family is mentioning. Okay? So, J. esperi qui vos discuteris divantage. I don't know what is that. Maybe French language or what Italian language, I don't know. So, there's no questions. Again, this is Dr. RIPbE preaching engineering for nation building. Thank you.